Welcome to Nap Labs, where we explore the universe slowly, gently, and deeply. Tonight, we journey to a world so strange that it breaks the rules we thought we understood. Jupiter, the giant that radiates more heat than it receives from the sun. The storm that has raged for centuries without fading. The magnetic fortress that shouldn't exist. This is the planet that physics can't fully explain. And as we drift through its mysteries together, let the questions carry you softly into rest, into wonder, into the quiet enormity of what we still don't know. Close your eyes if you wish. Breathe slowly. We're going to float through the solar system together, moving outwards from our small blue world, past the rust-colored deserts of Mars, through the asteroid belt where millions of ancient rocks tumble in the darkness, and out toward something magnificent, something vast, something that has puzzled scientists for generations and continues to whisper secrets we cannot yet hear. 5 times farther from the sun than Earth, orbiting in the cold deep beyond the inner solar system, there exists a world so large that all the other planets could fit inside it with room to spare. Jupiter, named for the king of the Roman gods, and rightfully so. This is a planet of superlatives, a place where the familiar rules of planetary science bend and sometimes break entirely. And tonight, we're going to understand why. Not quickly, not urgently, but slowly. Let's begin with something simple, something you can picture. Imagine Earth, our home, with its oceans and continents, its mountains and valleys, its delicate atmosphere wrapped around it like tissue paper. Now imagine placing more than 1,300 Earths inside a single sphere. That sphere is Jupiter. It is so massive that its volume could contain our entire world 1,321 times over. And yet, despite this enormity, despite being the largest planet in our solar system by far, Jupiter is not even close to being a star. It would need to be about 80 times more massive to ignite nuclear fusion in its core and shine with its own light. Instead, it exists in a strange middle ground, too large to be an ordinary planet, too small to be a star, radiating heat from its interior while simultaneously being classified as a failed star by some astronomers and a perfect example of a gas giant by others. This is where the mysteries begin. This is where physics starts to stumble. All planets spin, rotating on their axes as they orbit the sun, but Jupiter spins faster than any other planet in our solar system. Despite being more than 11 times wider than Earth, it completes a full rotation in just under 10 hours, 9 hours, 55 minutes, and 30 seconds. Imagine that. A world so vast that light would take several seconds to travel from one side to the other, yet it whirls through space at such speed that its day is less than half as long as ours. This rotation creates forces, tremendous centrifugal forces that make Jupiter bulge at its equator. If you could somehow stand on the cloud tops near Jupiter's equator, though of course you cannot stand on gas, you would be moving at a speed of approximately 45,000 kilometers per hour relative to the planet's center. And this speed, this violent rotation, shapes everything about Jupiter, from its bands of clouds to its powerful magnetic field, to the strange way heat moves through its interior. The first mystery, the one that gives this video its title, concerns heat, energy, and temperature, the laws of thermodynamics that govern how warmth flows through the universe. Every planet in our solar system receives energy from the sun. Sunlight falls on each world according to a simple principle called the inverse square law. Double your distance from the sun, and you receive 1/4 of the light and heat. Jupiter orbits at an average distance of 5.2 astronomical units from the sun. 1 astronomical unit is the distance between Earth and the sun, about 150 million kilometers. So Jupiter sits roughly 780 million kilometers from our star, receiving only about 4% of the sunlight that Earth receives. At that distance, the sun appears smaller in Jupiter's sky, about 1/5 the diameter it shows from Earth, and the warmth it provides is feeble, distant, almost negligible. And yet, when we point our infrared telescopes at Jupiter, when we measure the heat radiating from its clouds and upper atmosphere, we find something that shouldn't be there. Jupiter emits more energy than it receives, significantly more. The planet radiates about 67% more heat into space than it absorbs from the sun. If you were to add up all the sunlight falling on Jupiter's enormous surface and compare it to all the infrared radiation streaming away from the planet, the numbers don't balance. Jupiter glows with internal warmth, like a coal that has not yet finished cooling, like a world with its own furnace deep inside. This puzzled scientists for decades. Where does this extra heat come from? On Earth, our internal heat is the remnant of the planet's formation 4.6 billion years ago, combined with radioactive decay in the mantle and core. Uranium, thorium, and potassium slowly break apart over millions of years, releasing energy that keeps our planet's interior molten and drives plate tectonics and volcanism. But Jupiter is different. Jupiter is mostly hydrogen and helium, the lightest elements in the universe, with only a small rocky core at its center. There isn't enough radioactive material to account for the extra heat. And while Jupiter does have leftover warmth from its formation, the planet should have cooled down much more over 4.5 billion years than it appears to have done. The answer, scientists believe, lies in a process called helium rain. Deep inside Jupiter, where the pressure rises to millions of times Earth's atmospheric pressure, where the temperature climbs to tens of thousands of degrees, hydrogen behaves in ways that seem almost impossible. It becomes metallic. Under such extreme conditions, hydrogen atoms are squeezed so tightly together that their electrons break free and flow like electrons in a metal, conducting electricity, creating strange new forms of matter that we cannot replicate in any laboratory on Earth. And in this metallic hydrogen, ocean, helium, which is slightly heavier, doesn't mix evenly. It separates. It condenses into droplets. And these droplets, like raindrops in Earth's atmosphere, fall slowly downward through thousands of kilometers of metallic hydrogen, releasing gravitational potential energy as they sink toward the planet's core. Imagine that. Deep below the visible clouds of Jupiter, deeper than any ocean on Earth, deeper than the distance from New York to Los Angeles, there exists an ocean made of liquid metallic hydrogen, and through it, helium rain falls eternally, each droplet generating a tiny amount of heat as it descends. Multiply that heat by countless trillions of droplets, falling continuously for billions of years, and you begin to understand where Jupiter's extra warmth originates. It is the heat of differentiation, the slow sorting of elements by density, a process that will continue for billions of years into the future, gradually separating Jupiter's helium from its hydrogen in a cosmic distillation that powers the planet's glow. But this raises new questions. How much helium rain falls? How fast do the droplets sink? What is the structure of Jupiter's interior? And how do we know any of this is true? We cannot drill into Jupiter. We cannot send a probe to its core. The pressure would crush any spacecraft long before it reached the depths where helium condenses. And yet, we have clues. We have measurements. We have spacecraft that have visited Jupiter and instruments that have peered into its atmosphere with exquisite precision. Let's drift back in time for a moment. Let's trace the history of how we came to know Jupiter, how a bright point of light in Earth's night sky gradually transformed into one of the most studied and least understood worlds in our solar system. Ancient cultures knew Jupiter well. It was one of the 5 wandering stars, the planets visible to the naked eye, moving slowly against the background of fixed stars. The Babylonians tracked its motion across the zodiac. The Greeks called it Zeus, the supreme deity. The Romans renamed it Jupiter, and that name has endured for 2 millennia. But for most of human history, Jupiter remained a mystery, a light in the sky, a celestial wanderer whose nature was utterly unknown. Then, in the winter of 1610, Galileo Galilei pointed a new invention toward Jupiter, the telescope, a simple tube with glass lenses that magnified distant objects. And through it, Galileo saw something that changed everything. Jupiter was not a point of light. It was a disk. A tiny disk, yes, but a disk nonetheless, with structure and detail. And orbiting around Jupiter, moving night by night, were 4 smaller points of light. Moons. Galileo had discovered the 4 largest moons of Jupiter, now called the Galilean moons in his honor: Io, Europa, Ganymede, and Callisto. These moons orbit Jupiter, just as our moon orbits Earth, and their existence proved something profound. Not everything in the cosmos revolves around Earth. Here was a clear demonstration that other centers of motion exist, that the universe is more complex and more beautiful than the geocentric models of the ancient world had suggested. Over the centuries that followed, astronomers studied Jupiter with ever more powerful telescopes. They discovered its bands of clouds, alternating light and dark stripes that circle the planet parallel to its equator. They discovered the Great Red Spot, an enormous storm larger than Earth, a cyclone that has persisted for at least 350 years, and possibly much longer. They measured Jupiter's rotation period, noted how quickly it spins, and realized that this rapid rotation creates powerful winds, jet streams that blow at hundreds of kilometers per hour, shaping the cloud bands into their distinctive pattern. But telescopes can only reveal so much. To truly understand Jupiter, we needed to go there. We needed to send spacecraft across the vast gulf of space, through the asteroid belt, and into orbit around this giant world. And so we did. Beginning in the 1970s, humanity launched a series of missions to the outer solar system, and Jupiter was often the first stop. Pioneer 10, launched in 1972, became the first spacecraft to fly past Jupiter, passing within 130,000 kilometers of the cloud tops in December 1973. It sent back images that showed Jupiter's clouds in stunning detail, revealed the planet's intense radiation belts, and measured the magnetic field, discovering that Jupiter's magnetosphere is enormous, extending millions of kilometers into space, far larger than the Sun itself. if it were visible to the human eye. Pioneer 11 followed a year later, flying closer to Jupiter and providing more data, more images, more mysteries. Then came Voyager 1 and Voyager 2, launched in 1977, taking advantage of a rare alignment of the outer planets that occurs only once every 176 years. Voyager 1 reached Jupiter in March 1979, and the images it returned were breathtaking. The Great Red Spot appeared in vivid detail, a swirling maelstrom of clouds large enough to swallow 2 or 3 Earths. The cloud bands showed intricate structure, with smaller storms and vortices embedded within them. And perhaps most surprisingly, Voyager 1 discovered that Jupiter has a ring system, thin and faint, made of dust particles probably knocked off the planet's inner moons by micrometeorite impacts. Voyager 2 arrived 4 months later and added more observations, more data, more pieces to the puzzle. But these were flybys, brief encounters. The spacecraft swept past Jupiter in a matter of days or weeks, gathering data as quickly as possible before continuing their journeys to the outer planets and eventually to interstellar space. What we needed was a spacecraft that could stay at Jupiter, orbiting the planet for years, studying it in depth, watching its atmosphere change over time. And so, in October 1989, NASA launched Galileo. The Galileo mission was ambitious. It consisted of an orbiter designed to circle Jupiter for several years and a small probe designed to plunge into Jupiter's atmosphere, measuring temperature, pressure, composition, and wind speed as it descended. Galileo took a long, winding path to Jupiter, flying by Venus once and Earth twice to gain speed through gravitational assists, finally arriving at Jupiter in December 1995. As the spacecraft approached, it released the atmospheric probe, which entered Jupiter's atmosphere at a speed of nearly 180,000 kilometers per hour, experiencing deceleration forces of 230 times Earth's gravity. The heat shield glowed white-hot, protecting the delicate instruments inside, and then a parachute deployed, slowing the probe's descent. For 57 minutes, the probe fell through Jupiter's clouds, transmitting data back to the Galileo orbiter, which in turn relayed the information to Earth. 57 minutes might not sound like much, but during that time, the probe descended 156 kilometers into the atmosphere, deeper than anyone had expected, reaching pressures of 22 bars, 22 times the pressure at Earth's surface, and temperatures of 153 degrees Celsius. The data it sent back was astonishing. Jupiter's atmosphere at the probe's entry site was surprisingly dry, with less water than expected. The winds increased with depth rather than decreasing, blowing faster the deeper the probe fell. And then, at a depth of 156 kilometers, the probe's signal stopped. It had either been crushed by the pressure, melted by the heat, or simply lost radio contact with the orbiter overhead. In any case, it was gone, swallowed by the planet it had traveled for 6 years to reach. The Galileo orbiter, meanwhile, began its mission in earnest. For nearly 8 years, from December 1995 to September 2003, Galileo orbited Jupiter, making 34 close flybys of the planet and its moons. It studied the Great Red Spot in detail, watching the storm evolve, shrink, and change color. It discovered evidence of liquid water oceans beneath the icy surfaces of Europa, Ganymede, and Callisto. It observed volcanic eruptions on Io, the most volcanically active world in the solar system, and it measured Jupiter's magnetic field with unprecedented precision, revealing that the field is tilted relative to the planet's axis of rotation and that it wobbles slightly as Jupiter spins, a phenomenon that suggests the field is generated deep inside the planet, in the region where metallic hydrogen conducts electricity. But even Galileo, with all its discoveries, with all its years of observation, could not answer every question. In fact, the more we learned about Jupiter, the more questions emerged. Why does the Great Red Spot persist for centuries when similar storms on Earth dissipate in days or weeks? What drives the jet streams that create Jupiter's banded appearance? How deep do these winds extend? Are they shallow features, confined to the upper atmosphere, or do they penetrate thousands of kilometers into the planet's interior? And what about Jupiter's interior structure? How large is the rocky core? Is there even a distinct core? Or does the planet transition gradually from gas to liquid to solid as you descend? To answer these questions, NASA needed a new mission, a mission designed specifically to study Jupiter's deep interior, to peer beneath the clouds and measure the planet's composition, gravity field, and magnetic field with exquisite accuracy. And so, in August 2011, NASA launched Juno. Juno is a spacecraft unlike any other sent to Jupiter. While previous missions entered orbit around the planet's equator, circling in the same plane as the moons, Juno was designed to orbit over the poles, diving repeatedly from north to south, passing just a few thousand kilometers above the cloud tops at its closest approach. This polar orbit allows Juno to map Jupiter's gravitational and magnetic fields in 3 dimensions, building up a detailed picture of the planet's interior structure. And because Juno passes so close to Jupiter during each orbit, it experiences the planet's gravity more strongly. And these tiny variations in gravity reveal how mass is distributed inside the planet. Juno arrived at Jupiter on July 4, 2016, executing a nail-biting 35-minute engine burn to slow down and enter orbit. Since then, it has completed more than 50 orbits, and the data it has sent back has rewritten our understanding of Jupiter. Juno discovered that Jupiter's gravity field is not perfectly symmetric. The planet is lopsided in subtle ways, with mass distributed unevenly in the interior. This suggests that the core, if there is a distinct core, is not a simple ball of rock and ice, but rather a diffuse region where heavy elements are mixed with hydrogen and helium, creating a fuzzy core that lacks sharp boundaries. Juno also found that Jupiter's jet streams, the powerful winds that create the cloud bands, extend far deeper than anyone expected. By measuring tiny variations in the gravitational field caused by the jet streams themselves, scientists calculated that the winds penetrate at least 3,000 kilometers into the planet, roughly 1/20th of Jupiter's radius. Below that depth, the winds fade away, and the interior rotates as a solid body, all moving together at the same rate. But why do the winds stop at 3,000 kilometers? What causes them to fade? The answer appears to be related to the transition to metallic hydrogen. At the depth where hydrogen becomes metallic, where it starts to conduct electricity, the magnetic field generated in the deeper interior begins to interact strongly with the moving fluid, creating magnetic forces that suppress the winds and enforce uniform rotation. It is a beautiful example of how different physical processes interact, how magnetism and fluid dynamics and electrical conductivity all influence each other in the complex environment of a giant planet. But perhaps Juno's most stunning discovery concerns Jupiter's magnetic field itself. Scientists knew from previous missions that Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's field at the surface. But Juno revealed that the field is far more complex than anyone imagined. Near the North Pole, the magnetic field is highly concentrated, forming a structure unlike anything seen on any other planet. Near the South Pole, the field is more spread out, more diffuse. And in between, there are patches where the field points in unexpected directions, regions where north and south seem to swap places. This complexity suggests that the dynamo generating Jupiter's magnetic field, the motion of electrically conducting metallic hydrogen deep inside the planet, is not a simple, orderly process, but rather a chaotic, turbulent flow with multiple regions of circulation. And this brings us to one of the deepest mysteries of Jupiter, one of the reasons why physics struggles to fully explain this planet. We do not have a complete theory of how planetary magnetic fields are generated. On Earth, we understand the basics. The outer core, made of liquid iron and nickel, circulates in complex patterns, driven by heat escaping from the solid inner core and by the planet's rotation. This moving, electrically conducting fluid generates electric currents, and those currents produce a magnetic field. The field, in turn, influences the flow of the fluid, and the whole system feeds back on itself in a process called a dynamo. But the details are enormously complicated. The equations that describe magnetohydrodynamics, the study of how magnetic fields interact with conducting fluids, are some of the most difficult in physics to solve. Even with modern supercomputers, we cannot fully simulate Earth's dynamo, let alone Jupiter's. Jupiter's dynamo is even more challenging because the conducting fluid is not iron, but metallic hydrogen, a substance that exists under conditions we cannot replicate in laboratories. We know metallic hydrogen exists inside Jupiter because the pressure is high enough, about 2 million bars or more. But we have never created it ourselves. Scientists have tried. They have compressed hydrogen in diamond anvil cells, squeezing tiny samples between two diamonds to pressures exceeding 4 million bars. And they have seen hints of metallic behavior, brief flashes of conductivity before the sample explodes or the diamonds shatter. But these experiments are fleeting, lasting nanoseconds or microseconds, nowhere near long enough to study the properties of metallic hydrogen in detail. So we must rely on theory, on quantum mechanical calculations that predict how hydrogen atoms should behave under extreme pressure. And those theories have uncertainties, approximations, and assumptions built into them. This means our understanding of Jupiter's interior is based partly on physics we understand well, and partly on educated guesses. We know Jupiter is made mostly of hydrogen and helium because spectroscopy, the study of light absorbed and emitted by atoms, tells us so. We know the planet's mass and radius because we can measure its gravitational pull on spacecraft and moons. We know the planet radiates more heat than it receives because infrared telescopes measure that heat directly. But when we try to connect these observations, when we try to build a model of Jupiter's interior, that explains all the data simultaneously, we run into problems. The models work reasonably well, but they have free parameters, numbers that we adjust to match the observations because we don't know their correct values from first principles. How much heavy element material is mixed into Jupiter's hydrogen and helium? How viscous is metallic hydrogen? How efficiently does heat flow through the interior? These are questions that our current physics cannot answer with certainty. And so Jupiter remains, in a very real sense, a planet that physics can't fully explain. Not because physics is wrong, but because the physics of extreme conditions, the physics of matter under millions of bars of pressure and tens of thousands of degrees of temperature, is still being worked out. Every mission to Jupiter, every new observation, every refinement in our theoretical understanding brings us closer to a complete picture. But we are not there yet. And that is part of what makes Jupiter so captivating. It is a laboratory for studying matter under conditions that cannot be achieved anywhere else in the solar system. It is a testing ground for theories of planetary formation and evolution. And it is a reminder that even in our own cosmic backyard, profound mysteries remain. Let's turn our attention now to something you can picture, something visible and tangible, the Great Red Spot. This storm has fascinated astronomers since it was first observed in the 17th century, though the exact date of its discovery is debated. Some historians credit Robert Hooke or Giovanni Cassini with the first sightings in the 1660s. Others argue that the storm we see today might not be the same one observed 350 years ago, that perhaps the original Great Red Spot faded and a new one formed. We may never know for certain, but what we do know is that for at least the past 150 years, ever since continuous telescopic observations became routine, the Great Red Spot has been a permanent fixture of Jupiter's southern hemisphere, a gigantic anticyclonic storm rotating counterclockwise, embedded in the planet's south equatorial belt. How large is the Great Red Spot? Today, it is about 16,000 kilometers wide, large enough to fit 1.25 Earths inside it, but it used to be larger. Historical records show that in the late 1800s, the storm was about 40,000 kilometers wide, large enough to swallow 3 Earths. Over the past century and a half, the Great Red Spot has been shrinking. Slowly, steadily, it has contracted, losing width at a rate of about 1,000 kilometers per decade. No one knows why. Some scientists think the storm is dying, that it will eventually fade away within the next few decades. Others believe it is simply going through a cycle, that it will stabilize or even begin growing again. The truth is, we don't know. We have only been watching Jupiter closely for a tiny fraction of the storm's lifetime. A century and a half might seem long to us, but to Jupiter, to a storm that may have raged for millennia, it is the blink of an eye. What keeps the Great Red Spot alive? On Earth, hurricanes and cyclones are powered by warm ocean water. Evaporation from the ocean surface pumps moisture and energy into the storm, and the storm intensifies, spinning faster, growing larger. But hurricanes on Earth last days or weeks, not centuries, because they eventually move over land or over cooler water, cutting off their energy source, and they dissipate. Jupiter has no solid surface. It has no oceans of water. So where does the Great Red Spot get its energy? How does it persist for so long? The answer is not entirely clear, but scientists have several ideas. One possibility is that the storm draws energy from the smaller storms around it. Jupiter's atmosphere is filled with smaller vortices, some cyclonic, some anticyclonic, swirling in the jet streams that flow east and west around the planet. When these smaller storms encounter the Great Red Spot, they can be absorbed, merged into the larger structure, adding their energy to the giant storm. This process, sometimes called vortex cannibalism, might explain how the Great Red Spot maintains itself over long timescales. It feeds on the turbulence around it, growing stronger by consuming its neighbors. Another possibility involves heat. Remember that Jupiter radiates heat from its interior, heat generated by helium rain and residual warmth from the planet's formation. This heat flows upward through the atmosphere, warming the clouds from below, and this warming can drive convection, the rising and sinking of air that creates thunderstorms and turbulence. The Great Red Spot might tap into this internal heat, using it to maintain its circulation, much like a hurricane uses warm ocean water. But the details are unclear. How efficiently does heat flow into the storm? Is the heat distributed evenly, or are there hot spots and cold spots? These are questions that require more observations, more data, more understanding of how energy moves through Jupiter's complex atmosphere. Juno has studied the Great Red Spot up close, passing directly over it during one of its orbits and using its microwave radiometer to peer beneath the visible clouds. The data revealed that the storm extends far deeper than the cloud tops, reaching at least 350 kilometers into the atmosphere. And the winds near the top of the storm blow at speeds up to 640 kilometers per hour, making it one of the most violent weather systems in the solar system. But even these measurements, impressive as they are, do not fully explain the storm. Why does it rotate counterclockwise? Why is it stable when other storms come and go? Why does it remain confined to a narrow band of latitude instead of drifting north or south? These are questions that push the boundaries of our understanding of atmospheric dynamics. Let us drift now to another mystery, one that has intrigued scientists since the first close-up images of Jupiter were returned by spacecraft. The colors. Jupiter is not a uniform ball of white or grey. It is a tapestry of colors, with bands of cream and tan, and ochre and brown and red, all swirling together in intricate patterns. The Great Red Spot itself is red, though its color has faded over the decades from a deep brick red to a lighter salmon pink. Other regions of the atmosphere show different hues. Some clouds are nearly white, others are dark brown or grey, and all these colors must come from chemicals in the atmosphere, from molecules that absorb certain wavelengths of light and reflect others. But which molecules? What causes Jupiter's clouds to be colored? The simple answer is that we don't know for certain. Jupiter's atmosphere is mostly hydrogen and helium, neither of which has any color. But mixed into this hydrogen and helium are trace amounts of other substances: methane, ammonia, water vapor, phosphine, hydrogen sulfide, and various complex organic molecules called tholins. These trace constituents, present in concentrations of parts per million or parts per billion, give Jupiter its colors. But the chemistry is complicated. Different molecules produce different colors, and those colors can change depending on temperature, pressure, and the amount of sunlight the molecules are exposed to. Ammonia ice, for example, forms white clouds high in Jupiter's atmosphere, where temperatures drop to about minus 145 degrees Celsius. These are the brightest, lightest colored features on the planet, the zones where rising air carries ammonia upward, where it condenses into ice crystals that reflect sunlight efficiently. Deeper in the atmosphere, below the ammonia clouds, the temperature rises and different compounds condense. Ammonium hydrosulfide, a compound formed from ammonia and hydrogen sulfide, creates brownish clouds. Water ice, or liquid water droplets, if they exist, would form even deeper, though Juno's data suggests that in some regions, the atmosphere is surprisingly dry, with less water than expected. But what about the red color of the Great Red Spot? What molecule creates that distinctive hue? For decades, scientists speculated that it might be phosphorus, dredged up from deeper layers of the atmosphere by the storm's circulation. Or perhaps sulfur compounds, or complex organic molecules created by the action of sunlight and lightning on simpler compounds. In recent years, laboratory experiments have shed some light on this question. Researchers have taken mixtures of ammonia and acetylene, gases known to exist in Jupiter's atmosphere, and exposed them to ultraviolet light, simulating the sunlight that bathes Jupiter's upper atmosphere. The result is a sticky, reddish-brown substance, a type of tholin, an organic molecule that forms when ultraviolet light breaks apart simple molecules and allows the fragments to recombine in new ways. When this material is spread on a surface and its color is compared to the color of the Great Red Spot, the match is good, though not perfect. This suggests that the red color of the Great Red Spot and other colored features on Jupiter might be caused by photochemistry, by the action of sunlight creating complex organic molecules in the upper atmosphere. But there are complications. If sunlight creates these colored molecules, why are they concentrated in certain regions and not others? Why is the Great Red Spot red while nearby clouds are white or brown? The answer might involve the dynamics of the storm. Perhaps the circulation of the Great Red Spot dredges up gases from deeper layers, bringing them into the sunlit upper atmosphere where photochemistry can occur. Or perhaps the storm's intense winds and turbulence create conditions that favor the formation of certain molecules over others. These are possibilities, hypotheses, educated guesses based on limited data. The full answer awaits more observations, more experiments, more patient detective work. And this uncertainty extends to many other aspects of Jupiter's atmosphere. We know the planet has lightning, detected by the Voyager and Galileo and Juno spacecraft. We see flashes of light in Jupiter's clouds, brief sparks of electricity that indicate thunderstorms. But Jupiter's lightning is strange. It is concentrated near the poles, unlike Earth's lightning, which occurs mostly in the tropics. And the lightning on Jupiter is far more powerful than on Earth, with individual bolts releasing up to 10 times more energy. What creates these powerful discharges? Is it related to the structure of Jupiter's clouds, to the way ice particles collide and generate static electricity? Or is it something else, some process unique to Jupiter's atmosphere? We know Jupiter has auroras, glowing curtains of light near the poles, similar to the northern and southern lights on Earth. But again, Jupiter's auroras are different. On Earth, auroras are caused by particles from the sun, carried by the solar wind, entering the upper atmosphere near the magnetic poles and colliding with oxygen and nitrogen atoms, causing them to glow. Jupiter's auroras are more complex. They are partly powered by the solar wind, yes, but they are also powered by material from Jupiter's moon Io. Io is the most volcanically active world in the solar system, constantly spewing sulfur dioxide gas into space, and some of this gas becomes ionized, electrically charged, and trapped in Jupiter's magnetic field. This ionized gas, called a plasma torus, orbits around Jupiter at the same distance as Io, and Jupiter's rapid rotation sweeps the plasma along, accelerating it to high speeds. Some of this plasma spirals inward along magnetic field lines, eventually crashing into Jupiter's upper atmosphere near the poles, creating brilliant auroras that glow in ultraviolet and infrared light. Let's take a moment to appreciate the strangeness of this. Jupiter is not just a planet. It is a system, a complex interplay of magnetic fields and plasma and moons and radiation and chemistry. The moons influence the planet influences the moons. Energy flows from one to another in ways that are still being understood. And all of this happens far from the sun, in the cold darkness of the outer solar system, on a world that is more alien, more unlike Earth than most people realize. Imagine you could somehow visit Jupiter. Imagine you could descend through its atmosphere, protected by an impossibly strong spacecraft that could withstand the pressures and temperatures and radiation. What would you see? At first, high above the cloud tops, you would see the planet's faint ring system, thin bands of dust particles orbiting in the plane of the equator. These rings are not like Saturn's rings, which are bright and icy and easily visible from Earth. Jupiter's rings are dark, made of microscopic dust grains, and they are visible only when backlit by the sun or illuminated at certain angles. But they exist, testament to the constant bombardment of Jupiter's inner moons by micrometeoroids, each impact blasting tiny particles into space, some of which spiral inward toward the planet, some of which spread out into rings. As you descend closer, you enter the upper atmosphere, where the density is so low that it barely qualifies as atmosphere at all. Here, the sky is black and the stars are visible even in daylight, though the sun shines brightly, small but intense. The temperature is cold, minus 160 degrees Celsius or colder, and the pressure is less than 1 millibar, less than 1,000th of the pressure at Earth's surface. But as you fall deeper, the density increases. The sky begins to brighten, scattering sunlight into a pale blue or orange hue. Clouds appear below you, first as faint wisps, then as thick layers. You pass through the ammonia ice clouds, white and reflective, and then into deeper layers where ammonium hydrosulfide forms brownish hazes. The temperature rises steadily. At a depth of about 50 kilometers below the cloud tops, the temperature reaches 0 degrees Celsius, the freezing point of water. If there are water clouds on Jupiter, they might be here, but you wouldn't see them from above. They would be hidden beneath the ammonia and ammonium hydrosulfide layers, invisible to telescopes and spacecraft cameras. The pressure is now several bars, several times the pressure at Earth's surface, and the atmosphere is thick, dense, more like a fluid than a gas. You continue to fall, 100 kilometers deep, 200. The pressure climbs to tens of bars, then hundreds. The temperature rises to hundreds of degrees Celsius. The distinction between gas and liquid begins to blur. At a depth of about 1,000 kilometers, the pressure reaches 100,000 bars, and the hydrogen around you is no longer a gas. It is a supercritical fluid, neither gas nor liquid, but something in between, a substance that flows like a liquid but expands like a gas. And you are still falling. At 2,000 kilometers, the pressure is 1 million bars, and the temperature is about 10,000 degrees Celsius. The hydrogen becomes metallic, its electrons flowing freely, conducting electricity, glowing with heat. You are now inside a sea of metallic hydrogen, an ocean that extends for tens of thousands of kilometers in every direction, an ocean that makes up most of Jupiter's mass. And in this ocean, helium rain falls, droplets of helium condensing and sinking toward the core, releasing heat as they go, heat that flows upward, eventually reaching the surface and radiating into space. If you could somehow survive this journey, if your spacecraft could withstand pressures that would crush diamond, temperatures that would vaporize any known material, you would eventually reach the core. But what is the core? Juno's data suggests it is not a simple sphere of rock and ice, but rather a fuzzy region where heavy elements, silicon and iron, and oxygen and carbon, are mixed with hydrogen and helium in a gradient that lacks clear boundaries. The core might extend outward from the center for 10 or 20,000 kilometers, accounting for perhaps 5 to 15 Earth masses of heavy material, though these numbers are uncertain. And at the very center, the pressure reaches 40 to 50 million bars, and the temperature climbs to perhaps 36,000 degrees Celsius, hotter than the surface of the sun. But you cannot visit Jupiter. No human will ever stand on its surface because it has no surface to stand on. Jupiter is a world of gradients, of smooth transitions, from thin gas to thick gas to liquid to something stranger still. And this is part of what makes it so difficult to understand. We think of planets as having layers, like Earth with its crust and mantle and core. But Jupiter's layers are not distinct. They blend into one another, and the boundaries between them are defined not by abrupt changes in composition, but by subtle shifts in the behavior of hydrogen under pressure. Let us drift outward again, back to the realm of the moons, back to the family of worlds that orbit Jupiter. We have mentioned the Galilean moons already, Io and Europa, and Ganymede and Callisto. But we have not truly explored them, have not felt the wonder of these places. Each of these moons is a world in its own right, unique, fascinating, shaped by the immense gravitational influence of Jupiter. Start with Io. This moon, the innermost of the Galilean satellites, orbits just 422,000 kilometers from Jupiter, completing one orbit every 42.5 hours. It is slightly larger than Earth's moon, with a diameter of 3,643 kilometers, and it is the most volcanically active world in the solar system. Not might be, is. Io's surface is constantly being resurfaced by volcanic eruptions that spew sulfur dioxide gas and molten silicate lava, eruptions so powerful that some plumes rise 300 kilometers above the surface, visible from space. When Voyager 1 captured the first images of Io in 1979, scientists expected to see a dead, cratered world like our moon. Instead, they saw a surface painted in yellows and oranges and reds, with no impact craters visible at all. The surface was too young, too active, being constantly renewed by volcanism. Why is Io so active? The answer is tidal heating. As Io orbits Jupiter, it is pulled by the planet's enormous gravity. But Io's orbit is not perfectly circular. It is slightly elliptical, made so by gravitational interactions with Europa and Ganymede, the other large moons. As Io moves closer to Jupiter and then farther away during each orbit, the strength of Jupiter's gravitational pull changes. This causes Io to flex, to stretch and compress like a rubber ball being squeezed and released. And this flexing generates heat, enormous amounts of heat, enough to melt Io's interior and drive continuous volcanism. Scientists estimate that Io generates about 2.5 trillion watts of heat from tidal flexing, more than 100 times the heat generated by all the volcanoes on Earth combined. This heat escapes through volcanic vents, some of which erupt continuously for years or decades. The Prometheus volcano, for example, has been erupting since at least 1979, spewing sulfur dioxide gas in a continuous plume. Other volcanoes erupt more episodically, sometimes violently, ejecting so much material that they create visible changes in Io's appearance within months. And all this volcanic activity pumps gas into space, creating the plasma torus we mentioned earlier, a donut-shaped cloud of ionized sulfur and oxygen that orbits Jupiter at Io's distance. But Io pays a price for its proximity to Jupiter. The radiation near Jupiter is intense. The planet's magnetic field traps high-energy particles, electrons and protons accelerated to nearly the speed of light, creating radiation belts far more dangerous than Earth's Van Allen belts. At Io's distance, the radiation dose is about 36,000 sieverts per day. For context, 5 sieverts is enough to kill a human. 36,000 sieverts per day would destroy any spacecraft not specifically designed to withstand such conditions, frying electronics, degrading materials, rendering instruments useless. This is why missions to Io are so challenging, why no spacecraft has ever orbited Io or landed on its surface. Move outward to Europa. This moon orbits at 671,000 kilometers from Jupiter, about 50% farther than Io, and it could not be more different. Europa is a world of ice. Its surface is a shell of frozen water, cracked and crisscrossed with linear features called lineae, ridges and grooves that stretch for hundreds or thousands of kilometers. There are very few impact craters on Europa's surface, suggesting that the surface is young, perhaps only 50 to 60 million years old, constantly being renewed by some process that erases craters over time. And beneath the ice, beneath a shell perhaps 10 to 20 kilometers thick, scientists believe there is an ocean, a global ocean of liquid water kept warm by tidal heating, much like Io but less extreme, because Europa orbits farther from Jupiter and experiences less tidal flexing. This ocean, if it exists, could be 100 kilometers deep, containing more water than all of Earth's oceans combined. And where there is liquid water, where there is energy from tidal heating, where there are chemicals dissolved in the water, there is the possibility of life. Not complex life, not fish or plants, but microbes, simple organisms that could metabolize chemicals and reproduce in the dark waters beneath Europa's ice. This is speculation, of course. We have no direct evidence of life on Europa, but the possibility is tantalizing enough that NASA and the European Space Agency are planning missions to Europa in the coming decades. Missions designed to study the Moon in detail, to analyze the composition of the surface ice, to measure the thickness of the ice shell, and perhaps someday to drill through the ice and explore the ocean below. Europa is difficult to study because, like Io, it orbits within Jupiter's intense radiation belts. The radiation at Europa's distance is about 5,400 sieverts per day, still lethal to humans and damaging to spacecraft, though less severe than at Io. Any mission to Europa must be designed to withstand this radiation, using shielding and radiation-hardened electronics to survive long enough to complete its observations. Outward again, to Ganymede. This is the largest moon in the solar system, larger than Mercury, with a diameter of 5,268 kilometers. Like Europa, Ganymede has a surface of water ice, but Ganymede is old. Its surface shows two distinct types of terrain: dark terrain, heavily cratered, ancient, dating back billions of years, and bright terrain, grooved and ridged, younger, possibly formed by tectonic activity or cryovolcanism, the eruption of water or slush instead of molten rock. Ganymede also has its own magnetic field, the only moon in the solar system known to have one, suggesting that it has a liquid iron core, a dynamo generating a magnetic field much like Earth's, but weaker. And Ganymede, like Europa, may have an ocean beneath its icy crust. In fact, scientists believe Ganymede has multiple layers of ice and liquid water, stacked like a sandwich, with high-pressure forms of ice separating the layers. This structure is possible because of Ganymede's size and the immense pressure in its interior. At sufficient pressure, water ice transforms into different crystalline structures, forms of ice that are denser than liquid water and that sink rather than float. So Ganymede might have an ocean at a depth of 150 kilometers, then a layer of high-pressure ice, then another ocean, then another layer of ice, and so on. A complex internal structure unlike anything on Earth. Finally, Callisto, the outermost Galilean moon, orbiting at 1,883,000 kilometers from Jupiter, roughly the same distance as our moon from Earth. Callisto is heavily cratered, the most cratered object in the solar system. Its surface a record of billions of years of impacts. Unlike the inner moons, Callisto does not experience significant tidal heating. Its orbit is too circular, too distant from Jupiter, so there is no flexing, no internal heat source beyond the slow decay of radioactive elements. And yet, even Callisto may have an ocean, a deep subsurface ocean kept liquid by the residual heat from the moon's formation and by radioactive decay. The evidence is indirect, based on measurements of Callisto's magnetic field, but it suggests that somewhere between 100 and 200 kilometers beneath the surface, there is a layer of salty liquid water. So 3 of the 4 Galilean moons, Europa and Ganymede, and possibly Callisto, may have oceans beneath their icy surfaces. And all of this exists because of Jupiter. The planet's gravity shapes the orbits of these moons, causes tidal heating, generates the magnetic field that creates the radiation belts. Jupiter is not just a planet. It is the center of a complex system, a miniature solar system in its own right, with dozens of moons, some large, some small, all influenced by the giant at the center. Beyond the Galilean moons, Jupiter has dozens of smaller satellites. As of the year 2025, astronomers have discovered 95 moons orbiting Jupiter, though that number will likely continue to grow as surveys find fainter and fainter objects. Most of these smaller moons are irregular, meaning they have eccentric orbits that are tilted relative to Jupiter's equator, and many of them orbit in the retrograde direction, opposite to the direction Jupiter rotates. These characteristics suggest that the irregular moons were not formed in orbit around Jupiter, but were captured from elsewhere, asteroids or comets that wandered too close to Jupiter and were snared by its gravity. Some of these irregular moons are grouped into families, clusters of moons with similar orbits, suggesting they were once part of a larger body that was shattered by a collision. The Himalaya group, for example, consists of several small moons orbiting at about 11 million kilometers from Jupiter, all with similar inclinations and eccentricities, probably fragments of a single parent body that broke apart long ago. The Calm group and the Ananke group are similar families, orbiting even farther from Jupiter at distances of 20 to 30 million kilometers, at the outer edge of Jupiter's gravitational sphere of influence. These distant moons are tiny, only a few kilometers across, irregular in shape, and dark, reflecting very little sunlight. They're difficult to study, difficult to observe, often requiring large telescopes and long exposures to even detect. But they are part of Jupiter's story, part of the history of how the planet formed and how it interacted with the early solar system. When Jupiter first formed 4.5 billion years ago, the solar system was a chaotic place, filled with leftover material from the sun's formation, planetesimals and protoplanets colliding and merging and scattering. Jupiter's immense gravity influenced the orbits of countless objects, flinging some into the outer solar system, capturing others into orbit around itself. The irregular moons are relics of that time, frozen witnesses to an era of violence and chaos that shaped the solar system into the orderly place it is today. And Jupiter continues to influence the solar system. Its gravity perturbs the orbits of asteroids, sending some toward the inner solar system, where they occasionally collide with Earth or Mars or Venus. Jupiter has been called the vacuum cleaner of the solar system because it intercepts and captures or deflects many comets and asteroids that would otherwise reach the inner planets. In 1994, astronomers watched as comet shoemaker Levy 9 broke apart and collided with Jupiter, the fragments slamming into the planet's atmosphere over the course of a week, creating enormous dark scars in the clouds, each impact releasing energy equivalent to millions of nuclear bombs. This event demonstrated Jupiter's role as a shield, absorbing impacts that might otherwise strike Earth. But Jupiter's influence is not always protective. Sometimes Jupiter's gravity can send objects inward toward the Sun, increasing the likelihood of collisions with inner planets. The net effect is complex, and scientists continue to study how Jupiter has shaped the history of life on Earth, how its presence has influenced the bombardment of comets and asteroids over billions of years. Let's return to Jupiter itself, to the atmosphere, to the question of what lies beneath the clouds. We have talked about the great red spot, about the colors and the lightning and the winds, but we haven't talked about the vertical structure of the atmosphere, about how temperature and pressure change with depth, about where the different cloud layers form. This is a subject that requires patience and careful attention because it reveals how alien Jupiter truly is. Imagine dividing Jupiter's atmosphere into layers, like the layers of Earth's atmosphere. On Earth, we have the troposphere, where weather occurs, the stratosphere, where ozone absorbs ultraviolet light, the mesosphere, where meteors burn up, and the thermosphere and exosphere, the uppermost layers that gradually fade into space. Jupiter has similar layers, but they are defined differently by different processes and different chemical transitions. At the very top, in the exosphere, the atmosphere is so thin that atoms and molecules can escape into space. Hydrogen atoms, the lightest and fastest, occasionally reach speeds high enough to overcome Jupiter's gravity and drift away, though this loss is negligible over the age of the solar system. Jupiter's gravity is simply too strong for the planet to lose a significant fraction of its atmosphere. Below the exosphere is the thermosphere, where temperatures rise due to absorption of ultraviolet and X-ray radiation from the sun. This might seem counterintuitive. Shouldn't the temperature drop as you move away from the heat source, away from the deeper, warmer layers? But in the thermosphere, the atmosphere is so thin that there are very few collisions between atoms, and the few atoms that are present can be heated to high temperatures by solar radiation without significantly warming the surrounding gas. On Jupiter, thermospheric temperatures can reach 1,000 degrees Celsius or more, even though the atmosphere at this altitude is essentially a vacuum, with a density far lower than the best laboratory vacuums on Earth. Descending through the thermosphere, we reach the stratosphere, where temperatures are relatively stable or decrease slowly with altitude. In Jupiter's stratosphere, hydrocarbons form. Methane, present in trace amounts, is broken apart by ultraviolet light, and the fragments recombine to form ethane, acetylene, and other more complex organic molecules. These hydrocarbons create a haze, a layer of smog that absorbs sunlight and influences the temperature structure of the upper atmosphere. Juno detected ammonia in Jupiter's stratosphere, a surprising finding because ammonia should freeze out at colder temperatures deeper in the atmosphere. The presence of stratospheric ammonia suggests that powerful storms or other dynamic processes are lofting ammonia upward from the deeper layers, carrying it into regions where it normally wouldn't exist. Below the stratosphere is the troposphere, the weather layer, where clouds form and winds blow and storms churn. This is the region we see when we look at Jupiter through a telescope, the colorful bands and swirls and spots. The base of the troposphere, the deepest we can observe directly, is defined by the pressure at which water would condense into clouds, about 5 to 10 bars, roughly 100 kilometers below the visible cloud tops. But as we discussed earlier, some regions of Jupiter's atmosphere are dry, with less water than expected, so the water cloud layer might be patchy or absent in certain areas. The troposphere is where ammonia condenses into ice crystals, forming the bright white zones at altitudes where the temperature is about minus 145 degrees Celsius. Below the ammonia clouds, ammonium hydrosulfide forms the brownish layers, and below that, if there is enough water, liquid water droplets or ice crystals form the deepest clouds. And between these layers, there are regions of clear gas, transparent windows, where you could theoretically see deeper into the planet, if only you could get a spacecraft into the right position The winds in the troposphere are organized into jet streams, alternating eastward and westward flows that circle the planet parallel to the equator. The zones, the bright bands, are regions of upwelling, where gas rises, cools, and forms clouds. The belts, the dark bands, are regions of downwelling, where gas sinks, warms, and evaporates clouds, revealing the darker, deeper layers beneath. This circulation is driven partly by Jupiter's internal heat and partly by the Coriolis effect, the apparent deflection of moving objects caused by the planet's rotation. But the details are complex, involving interactions between the winds and the magnetic field and the internal structure, interactions that we are only beginning to understand. There is something mesmerizing about Jupiter's atmosphere, something almost hypnotic in the way the clouds flow and merge and swirl. If you watch time-lapse videos of Jupiter, assembled from images taken over hours or days or weeks, you see motion everywhere. Vortices spin, some clockwise, some counterclockwise, depending on whether they are cyclonic or anticyclonic. Cloud features stretch and shear, pulled apart by the differential winds. Smaller storms collide with larger storms, sometimes merging, sometimes bouncing off each other like billiard balls. And through it all, the jet streams remain stable, unchanging, persistent features that have existed for as long as we have been observing Jupiter. This persistence is part of the mystery. On Earth, jet streams meander, shifting north and south with the seasons, influenced by the distribution of continents and oceans and ice caps. But Jupiter has no continents, no seasons in the sense we experience them. Its axis of rotation is tilted only about 3 degrees relative to its orbital plane, so there are no significant seasonal variations in sunlight. The jet streams on Jupiter are fixed at specific latitudes, unchanging, and we don't fully understand why. What determines the location of these jets? Why are there some latitudes with strong jets and other latitudes with weak or absent flows? These questions relate to the deep structure of the planet, to how energy is transported from the interior to the surface, and to how the magnetic field interacts with the atmospheric circulation. And as with so many aspects of Jupiter, the answers are incomplete. Juno has provided new insights by measuring the gravity field with such precision that it can detect the mass of the jet streams themselves. The winds carry momentum, and momentum has mass in a sense, a gravitational signature that shows up as tiny anomalies in the gravity field. By mapping these anomalies, scientists have determined that the jet streams extend about 3,000 kilometers deep, as we mentioned earlier, but the measurements also reveal asymmetries. The northern and southern hemispheres of Jupiter are not identical. The jets are not perfectly symmetric. There are subtle differences in wind speed, in cloud morphology, in the distribution of storms. And these differences hint at deeper asymmetries in the planet's interior, asymmetries that we are only beginning to detect. One of the most striking discoveries from Juno concerns the poles. Before Juno, we had never seen Jupiter's poles clearly. The Voyager and Galileo spacecraft orbited near the equator, and from Earth, Jupiter's poles are tilted almost edge-on to us, making them difficult to observe. But Juno's polar orbit carries it directly over the north and south poles on every orbit, and the images it has returned are stunning. The poles are chaotic, filled with cyclones, massive storms spinning like pinwheels, arranged in geometric patterns that seem almost too orderly to be natural. At the North Pole, there is a central cyclone surrounded by a ring of 8 other cyclones, all spinning counterclockwise, all roughly the same size, all maintaining their positions relative to one another. At the South Pole, there is a similar pattern, a central cyclone surrounded by 5 others, arranged in a pentagon. These polar cyclones are enormous, each one about 4,000 to 5,000 kilometers across, about the size of the United States. And they are persistent, stable, showing little change over the years that Juno has been observing them. Why do they arrange themselves in these geometric patterns? Why don't they merge or drift apart? Scientists believe the answer involves a balance between the Coriolis effect, which causes cyclones to repel each other, and the tendency of vortices to merge when they get too close. The result is a stable configuration where the cyclones maintain a certain separation, locked into a pattern by the dynamics of rotating fluids. But this is a tentative explanation, a hypothesis that requires further testing and modeling. Let's pause for a moment. Let's take a deep breath and let the enormity of Jupiter settle over us like a soft, heavy blanket. We have been discussing numbers, measurements, chemical compositions, physical processes, all the technical details that scientists use to understand the universe. But underneath all of this, there is something deeper, something that goes beyond equations and data. There is the simple, profound fact that Jupiter exists, that a world so alien, so unlike anything we can directly experience, is out there, orbiting the sun, following the same laws of physics that govern our own world, and yet manifesting those laws in ways that seem almost magical. Jupiter is a reminder of the diversity of the universe, of the endless creativity of nature. It is easy to fall into the trap of thinking that Earth is the template, that planets should be rocky with solid surfaces and nitrogen-oxygen atmospheres and liquid water oceans. But Jupiter shows us that planets can be so much more. They can be vast spheres of gas and liquid with magnetic fields strong enough to trap radiation belts that would kill any life we know, with storms that rage for centuries, with moons that have subsurface oceans, with rings and auroras and lightning and chemistry that we are only beginning to explore. And Jupiter is just one planet, one world among thousands that we have discovered orbiting other stars, among billions that must exist in our galaxy alone. Each one is unique, shaped by its history, by the conditions in which it formed, by the interplay of gravity and rotation and magnetic fields and chemistry. If we can barely understand Jupiter, a planet in our own solar system, a planet we have visited with multiple spacecraft, how much more mysterious are the worlds orbiting distant stars, worlds we can only detect as tiny dips in starlight or subtle wobbles in a star's motion. This is the beauty of science. It is not about having all the answers. It is about asking questions, about being comfortable with uncertainty, about pursuing knowledge with patience and humility. Every answer leads to new questions. Every mystery we solve reveals deeper mysteries waiting beneath. And Jupiter, the giant that physics can't fully explain, is a perfect example of this endless process of discovery. Let us turn now to the question of how Jupiter formed. This is a story that takes us back to the very beginning of the solar system, to a time 4.6 billion years ago when the Sun was just forming, when the region around the young star was filled with a disk of gas and dust, the raw material from which planets would eventually coalesce. The prevailing theory of planet formation, called the core accretion model, suggests that planets form in stages. First, dust grains in the protoplanetary disk collide and stick together, building up larger and larger particles. These particles settle toward the midplane of the disk, forming a thin layer of material where collisions are more frequent. Over time, kilometer-sized bodies called planetesimals form, then 10-kilometer-sized bodies, then 100-kilometer-sized bodies, growing by accumulation, by gravitational attraction, by collisions that merge smaller objects into larger ones. In the inner solar system, close to the Sun, it is warm and only rocky material, silicates and metals, can condense into solid form. This is why the inner planets, Mercury and Venus, and Earth and Mars, are rocky. But beyond a certain distance from the Sun, called the snowline or ice line, it is cold enough for water and other volatile substances to freeze. At around 4 to 5 astronomical units from the Sun, roughly where Jupiter orbits today, water ice and other ices were abundant in the protoplanetary disk. And this made all the difference. With ice available, planetesimals could grow much larger, much faster. Ice was more abundant than rock, so there was more material to work with. A rocky core formed first, growing to about 10 Earth masses, and at that size, its gravity became strong enough to pull in gas directly from the surrounding disk. Hydrogen and helium, the most abundant elements in the disk, began to flow onto the growing planet, accelerating the growth process. The more gas the planet captured, the stronger its gravity became, and the faster it could capture even more gas. This runaway process continued until either the protoplanetary disk dissipated, blown away by the young Sun's stellar wind, or until the planet had captured all the nearby gas, leaving a gap in the disk. The result was Jupiter, a planet with a rocky, icy core surrounded by a massive envelope of hydrogen and helium. But the details of this process are uncertain. How quickly did Jupiter form? How large did the core grow before gas accretion began? Did Jupiter form where it is now? Or did it migrate inward or outward from its original location? These are questions that planetary scientists are actively researching, using computer simulations and observations of other planetary systems to test and refine the core accretion model. An alternative theory, called the disk instability model, suggests that Jupiter could have formed much more rapidly. If a region of the protoplanetary disk became dense enough, it might have collapsed directly into a planet without going through the slow process of building up a solid core first. This could explain why Jupiter is so massive, why it captured so much gas before the disk dissipated. But the disk instability model has challenges. It requires very specific conditions in the disk, conditions that may not have existed in the early solar system. Juno's measurements of Jupiter's gravitational field have shed some light on this question. By determining that Jupiter has a dilute, fuzzy core rather than a compact, well-defined core, Juno suggests that something disrupted the core after the planet formed. One possibility is a giant impact. Early in the solar system's history, while planets were still forming and the region around the Sun was crowded with planetesimals and protoplanets, Jupiter might have collided with another large body, perhaps an object with a mass of several Earths. Such a collision would have released enormous energy, partially disrupting Jupiter's core, mixing heavy elements into the surrounding hydrogen and helium, creating the diffuse structure we see today. This is speculative, but it is consistent with the data, and it highlights how violent and chaotic the early solar system was. Another question about Jupiter's formation concerns its location. Did Jupiter form where it is now, at 5.2 astronomical units from the Sun, or did it migrate? Migration is a common feature of planetary systems. As planets form and interact gravitationally with a disk of gas and dust, they can spiral inward or outward, sometimes traveling great distances from their original positions. Some of the exoplanets we have discovered around other stars are hot Jupiters, giant planets orbiting very close to their stars, completing an orbit in just a few days. These planets almost certainly did not form where they are now, because it would have been too hot for ice to condense, too hot for them to grow large enough to capture gas. Instead, they must have formed farther out and migrated inward, driven by interactions with the protoplanetary disk or by gravitational interactions with other planets. Did Jupiter migrate? Some models suggest that Jupiter did indeed migrate inward during its formation, moving from perhaps 7 or 8 astronomical units down to about 1.5 astronomical units, nearly as close to the Sun as Mars is today. Then, as Saturn formed and began interacting with Jupiter gravitationally, the two planets reversed course and migrated back outward, settling into their current orbits. This scenario is called the Grand Tack hypothesis, named after the sailing maneuver where a boat changes direction by turning into the wind. The Grand Tack hypothesis has interesting implications for the inner solar system. If Jupiter migrated inward and then outward, it would have scattered and ejected much of the material in the inner solar system, reducing the amount of material available to form planets. This might explain why Mars is so small, why it has only about 1/10 the mass of Earth. Jupiter's migration might have prevented Mars from growing larger by removing nearby planetesimals. It might also explain the structure of the asteroid belt, the region between Mars and Jupiter, filled with millions of small rocky bodies. These asteroids are leftovers from planet formation, material that never coalesced into a planet because Jupiter's gravity kept stirring things up, preventing accretion. But the Grand Tack hypothesis is controversial. Not all planetary scientists agree that it happened. The evidence is indirect, based on computer simulations and on the structure of the solar system as we see it today. Direct evidence of Jupiter's migration, such as specific chemical signatures in its atmosphere or unusual properties of its core, is difficult to obtain. And so the question remains open, another mystery to be solved by future observations and future missions. Let's talk about the magnetic field again, because it is one of Jupiter's most remarkable features and one that connects to so many other aspects of the planet. We mentioned earlier that Jupiter has the strongest magnetic field of any planet in the solar system. At the cloud tops near the equator, the field strength is about 4.3 Gauss, about 20,000 times stronger than Earth's field at our planet's equator. And the magnetosphere, the region of space dominated by Jupiter's magnetic field, extends outward for millions of kilometers, all the way to the orbit of Saturn in the direction away from the Sun. The magnetosphere is shaped by the solar wind, the stream of charged particles flowing outward from the Sun. On the side facing the Sun, the solar wind compresses the magnetosphere, pushing it closer to Jupiter. On the night side, the magnetosphere stretches out into a long tail, called the magnetotail, that extends for hundreds of millions of kilometers downstream. Inside the magnetosphere, trapped particles spiral along magnetic field lines, bouncing back and forth between the north and south poles, creating the intense radiation belts that make Jupiter such a hostile environment for spacecraft. The source of Jupiter's magnetic field is the dynamo in the metallic hydrogen layer deep inside the planet. As we discussed, the rapid rotation of Jupiter, combined with convective motions driven by heat flowing from the interior, creates a complex pattern of circulation in the metallic hydrogen. This circulation generates electric currents, and those currents produce the magnetic field. But the details of how this works are poorly understood. The equations that describe magnetohydrodynamics are nonlinear, meaning that small changes in conditions can lead to large changes in outcomes. Predicting the behavior of a dynamo requires solving these equations numerically, using supercomputers to simulate the flow of electrically conducting fluid in a rapidly rotating spherical shell. And even with modern computers, such simulations are challenging and time-consuming. Juno's measurements have revealed that Jupiter's magnetic field is more complex than Earth's. Earth's field is roughly a dipole, like a bar magnet, with field lines emerging from the south magnetic pole and looping around to enter the north magnetic pole. Jupiter's field has a strong dipolar component, but it also has significant higher-order components, quadrupole and octopole terms, that create regions where the field is stronger or weaker than a simple dipole would predict. Near the North Pole, there is a concentrated patch of intense magnetic field called the Great Blue Spot, though it has nothing to do with color. It is called blue because scientists assigned blue to regions of strong field when they created maps of Jupiter's magnetic field. This concentrated field suggests that the dynamo processes near the North Pole are different from those near the South Pole, perhaps due to differences in the flow patterns or the conductivity of the metallic hydrogen in those regions. Another surprising discovery from Juno is that Jupiter's magnetic field changes over time. By comparing Juno's measurements with measurements from earlier missions, scientists found that the field has shifted and evolved over the decades. The Great Blue Spot has moved, drifting eastward at a rate of about 2 degrees per year. This is much faster than Earth's magnetic field changes, which shift slowly over centuries and millennia. The rapid changes in Jupiter's field suggest that the dynamo is highly dynamic, with flows in the metallic hydrogen ocean changing on timescales of years to decades. What drives these changes? Are they related to variations in the heat flow from Jupiter's core? Are they caused by interactions between the magnetic field and the atmospheric winds? Are they random fluctuations, turbulent eddies in the metallic hydrogen that come and go unpredictably? We don't know. And this is one of the central mysteries of Jupiter, one of the reasons why the planet continues to challenge our understanding of physics. The magnetosphere of Jupiter interacts with the moons, particularly Io, in fascinating ways. We mentioned earlier that Io's volcanism pumps sulfur dioxide gas into space, and that some of this gas becomes ionized and trapped in Jupiter's magnetic field, forming a plasma torus. But the interaction is more complex than that. Io orbits inside Jupiter's magnetosphere, and as the magnetosphere rotates with the planet, it sweeps past Io at a relative speed of about 57 kilometers per second. This creates an electric field, and the electric field drives currents that flow between Jupiter and Io. Currents that carry millions of amperes of electric charge. These currents heat Io's atmosphere, cause additional ionization, and create glowing auroras in Io's tenuous atmosphere. They also create an auroral footprint on Jupiter itself. When you look at Jupiter's auroras in ultraviolet light, you see a bright spot connected to Io by magnetic field lines, a spot that moves as Io orbits the planet. Europa and Ganymede also create similar auroral footprints, though weaker, because they orbit farther from Jupiter and interact less intensely with the magnetosphere. This connection between Jupiter and its moons is an example of how electromagnetic forces can couple objects across vast distances. Io is not just passively orbiting Jupiter. It is electrically connected to the planet, part of a circuit that extends across hundreds of thousands of kilometers, a circuit that carries energy and momentum between the moon and the planet. And this interaction has consequences. The electrical currents exert a drag on Io, slowly robbing it of orbital energy, causing the moon to spiral inward toward Jupiter. The timescale for this inward migration is long, millions or billions of years, but it is happening. A slow, inexorable process driven by electromagnetism and gravity acting together. Let's drift now toward the future. What comes next for our exploration of Jupiter? What questions will future missions try to answer? And what new mysteries might we discover as we continue to study this giant world? NASA's Juno mission is currently extended through at least September 2025, and possibly longer if the spacecraft remains healthy. Each orbit brings Juno close to Jupiter. Each pass provides new data, new images, new measurements of the gravitational and magnetic fields. Juno has already transformed our understanding of the planet, and it will continue to do so for as long as it operates. Eventually, like Galileo before it, Juno will end its mission by plunging into Jupiter's atmosphere, burning up in the planet's clouds to avoid any possibility of contaminating Europa or the other potentially habitable moons with Earth microbes. But even before Juno's mission ends, new spacecraft are being prepared. The European Space Agency is developing the Jupiter Icy Moons Explorer, called JUICE, which launched in April 2023 and will arrive at Jupiter in July 2031. JUICE is designed to study Ganymede, Callisto, and Europa, making multiple flybys of each moon before finally entering orbit around Ganymede, the first spacecraft ever to orbit a moon of another planet. JUICE will carry cameras, spectrometers, radar instruments, and magnetometers, all designed to study the moon's surfaces, subsurface oceans, and interactions with Jupiter's magnetosphere. NASA is also preparing the Europa Clipper mission, which launched in October 2024 and will arrive at Jupiter in April 2030. Europa Clipper will not orbit Europa itself because the radiation environment is too harsh for a spacecraft to survive in orbit around the moon for long periods. Instead, It will orbit Jupiter and make nearly 50 close flybys of Europa, each flyby lasting only a few hours, minimizing the radiation dose while still allowing detailed observations. The spacecraft will carry ice-penetrating radar to measure the thickness of Europa's ice shell, thermal instruments to search for warm spots where the ocean might be close to the surface, and mass spectrometers to analyze any plumes of water vapor that might be erupting from cracks in the ice. These missions, JUICE and Europa Clipper, represent a new era in the exploration of Jupiter and its moons. They are focused not just on the planet itself, but on the moons, on the possibility of oceans and perhaps life. And if they find evidence that Europa or Ganymede or Callisto has the right conditions for life, if they detect organic molecules or chemical signatures that suggest biological processes, then the next step will be even more ambitious. Future missions might attempt to land on Europa, to drill through the ice, to send a submersible into the ocean below. This is decades away, perhaps half a century, but it is within the realm of possibility, within the scope of what humanity might achieve in our lifetimes or the lifetimes of the next generation. And what about Jupiter itself? Are there missions planned to study the planet's deep interior, to finally resolve the mysteries of the core, the metallic hydrogen, the helium rain? One concept that has been proposed is an atmospheric probe that would go deeper than Galileo's probe, descending hundreds of kilometers into Jupiter's atmosphere, measuring temperature, pressure, composition, and wind speed all the way down. Such a probe would need to be extremely robust, built to withstand pressures of hundreds or thousands of bars, temperatures of hundreds of degrees, and it would need to transmit data continuously as it fell, because once it reaches a certain depth, the pressure would crush it and the mission would end. Another concept involves multiple smaller probes dropped into different regions of Jupiter's atmosphere simultaneously, creating a network of measurements that could reveal how the atmosphere varies with latitude and longitude. This would help scientists understand the three-dimensional structure of Jupiter's weather, how storms interact, how energy flows from the interior to the surface, how the jet streams maintain themselves over time. There are also proposals for orbiters that would study Jupiter's magnetosphere in greater detail, spacecraft that would fly through the radiation belts, measure the plasma environment, observe the auroras from different angles. And there are ideas for missions to the Trojan asteroids, 2 clusters of asteroids that orbit the Sun at the same distance as Jupiter, one cluster leading Jupiter in its orbit, the other trailing behind. These asteroids are thought to be primitive, leftover material from the outer solar system, and studying them could reveal clues about the conditions in which Jupiter formed. But all of these missions are expensive, requiring billions of dollars and decades of planning and development. Space agencies must prioritize, choosing which missions to fund based on scientific merit, technological readiness, and available budget. And so, the exploration of Jupiter proceeds slowly, incrementally, one mission at a time, each one building on the discoveries of the previous missions, each one revealing new mysteries, even as it solves old ones. Let's take a moment to reflect on what we have learned, on the journey we have taken together through the Jovian system. We began with a simple question, a hook to draw you in. Why is Jupiter a planet that physics can't fully explain? And as we have explored the answer, we have discovered layer upon layer of complexity, mystery upon mystery. Jupiter radiates more heat than it receives, and we think we know why. Helium rain falling through metallic hydrogen, but we cannot be certain because we cannot see into the planet, cannot measure the processes directly. Jupiter's magnetic field is the strongest in the solar system, and we understand the basics of how dynamos work, but the details elude us. The complexity of magnetohydrodynamics exceeds our computational abilities. Jupiter's Great Red Spot has raged for centuries, and we have ideas about how it maintains itself, vortex cannibalism and internal heat. But we don't have a complete theory, a model that predicts every aspect of its behavior. Jupiter's interior structure is a gradient, a smooth transition from gas to liquid to something stranger. And we have measurements from Juno that constrain the possibilities. But the core remains fuzzy, uncertain, difficult to model. Jupiter's atmosphere is colored by chemistry we don't fully understand. Photochemistry creating complex organic molecules. But we don't know exactly which molecules produce which colors, and we can only make educated guesses. Jupiter's moons have subsurface oceans, kept warm by tidal heating, but we don't know how deep those oceans are, what their chemistry is, whether life could exist in their dark waters. This is the nature of science at the frontier. Uncertainty, incomplete knowledge, questions that lead to more questions. And it is beautiful. It is humbling. It reminds us that the universe is vast and complex, that we are still learning, still exploring, still discovering. Every answer we find is a gift, a small light illuminating a tiny corner of the darkness. And every question we cannot yet answer is an invitation, a challenge, a reminder that there is always more to learn. Jupiter, the giant that physics can't fully explain, stands as a monument to the limits of our understanding and to the boundless curiosity that drives us to push those limits, to reach farther, to ask deeper questions, to never stop seeking. And in that seeking, in that patient, humble exploration of the unknown, we find not just knowledge, but meaning, purpose, a connection to something larger than ourselves. Let us turn our thoughts now to the role Jupiter has played in shaping the solar system, in creating the conditions that allowed Earth to exist, that allowed life to emerge, that allowed us to be here, contemplating the cosmos. Because Jupiter is not just a distant world, separate from our own. It is part of a system, part of a delicate balance of gravitational forces and orbital resonances that have guided the evolution of the solar system for billions of years. When Jupiter formed, when it grew massive enough to dominate the outer solar system gravitationally, it began to influence the orbits of everything around it. Asteroids and comets that ventured too close were either captured into orbit around Jupiter, flung out of the solar system entirely, or redirected into new orbits that carried them toward the inner planets. This gravitational sculpting cleared out much of the material in the outer solar system, leaving behind the relatively empty space we see today beyond Jupiter's orbit, punctuated only by Saturn, Uranus, Neptune, and the scattered populations of icy bodies in the Kuiper Belt and Oort cloud. But Jupiter's influence extended inward as well. The asteroid belt, located between Mars and Jupiter, contains millions of rocky bodies, but their total mass is surprisingly small, less than 1/20th the mass of Earth's moon. Why is the asteroid belt so depleted? Why didn't these asteroids coalesce into a planet? The answer is Jupiter. The giant planet's gravity stirred the asteroid belt, increasing the relative velocities of asteroids, making collisions more destructive rather than constructive. Instead of sticking together and building a planet, asteroids in Jupiter's gravitational sphere of influence shattered each other, grinding themselves down into smaller and smaller fragments. And Jupiter's orbital resonances, locations where an asteroid's orbital period is a simple fraction of Jupiter's period, 1/2 or 1/3 or 2/5, are nearly empty, swept clear by gravitational perturbations that eventually eject asteroids from those orbits. This same process affects comets. The Oort cloud, a vast spherical shell of icy bodies surrounding the solar system at distances of thousands to tens of thousands of astronomical units, is the source of long-period comets. Comets that take thousands or millions of years to complete one orbit around the Sun. When these comets are nudged out of the Oort cloud by the gravitational influence of passing stars or the tidal force of the Milky Way galaxy, they fall inward toward the Sun, and some of them pass close to Jupiter. When they do, Jupiter's gravity can alter their orbits dramatically, either sending them back out to the Oort cloud, ejecting them from the solar system entirely, or redirecting them into shorter period orbits that bring them close to the Sun more frequently. This scattering of comets has had profound consequences for Earth. During the early history of the solar system, during the first few 100 million years, the inner planets were bombarded by comets and asteroids, impacts that delivered water and organic molecules, the building blocks of life. Some scientists believe that most of Earth's water came from comets, though others argue that it came from asteroids or was present in the planetesimals that formed Earth in the first place. The truth is probably a combination of all three sources. But Jupiter played a role in determining how many comets and asteroids struck Earth, how much water and organic material was delivered, and therefore in creating the conditions that allowed life to emerge. There is a delicate balance here. Too many impacts, and Earth's surface would have been sterilized repeatedly, the heat from impacts vaporizing oceans and atmospheres. Too few impacts, and Earth might have been dry, lacking the water necessary for life. Jupiter, by redirecting some comets and asteroids toward the inner solar system while ejecting others, helped to create the right balance, the right amount of bombardment to deliver water and organics without destroying the nascent biosphere. This role as a protector and a gardener, shaping the conditions for life while not overwhelming the inner planets, is sometimes called the Jupiter effect. But it is not a simple, one-sided relationship. Jupiter is not a benevolent guardian. It is a massive gravitational force indifferent to the consequences of its influence, simply following the laws of physics, the same laws that govern everything in the universe. And yet, the net result of Jupiter's existence has been, at least for Earth, beneficial. We are here, in part, because Jupiter is there. Imagine, for a moment, a solar system without Jupiter. What would it look like? How would it differ from the solar system we inhabit? This is a question that planetary scientists have explored using computer simulations, running virtual solar systems with different initial conditions, watching how they evolve over billions of years. In a solar system without Jupiter, the asteroid belt would be different. Without Jupiter's gravitational stirring, asteroids might have coalesced into one or more planets, creating a fifth terrestrial planet between Mars and what would have been the outer edge of the planetary system. This planet might have been similar in size to Earth or Mars, a rocky world with its own history of volcanism and tectonics, and perhaps even life. In a solar system without Jupiter, the bombardment of the inner planets would have been different. More comets and asteroids might have struck Earth and Mars and Venus, or fewer, depending on the distribution of material and the dynamical processes at work. The rate of impacts would have changed the history of these planets, accelerated or delayed the emergence of life, created conditions that were either more or less hospitable. In a solar system without Jupiter, the outer planets, Saturn and Uranus and Neptune, might not exist at all, or they might have formed in different locations, with different masses, with different moon systems. The delicate choreography of orbital resonances and gravitational interactions that shape the architecture of the outer solar system would have played out differently, creating a system that might be unrecognizable compared to the one we know. And in a solar system without Jupiter, humanity would not exist, at least not in the form we know today. The entire history of Earth, from its formation to the emergence of life, to the evolution of complex organisms, to the rise of intelligence and civilization, has been shaped in countless subtle ways by Jupiter's presence. We are the product of a specific history, a specific sequence of events, and Jupiter is woven into that history, an unseen thread connecting the outer solar system to the inner, the giant to the small, the ancient past to the present moment. Let's broaden our perspective now. Let's zoom out from Jupiter and the solar system and consider the universe as a whole. Because Jupiter is not unique, it is one example of a type of planet that is common throughout the galaxy. Gas giants and ice giants orbiting other stars, worlds that are similar to Jupiter in some ways and different in others. When astronomers first began detecting planets around other stars in the 1990s, the first planets they found were hot Jupiters, massive planets orbiting very close to their stars, completing an orbit in just a few days. These planets were easiest to detect because they cause large wobbles in their stars' motions and because they transit in front of their stars, blocking a measurable fraction of starlight. But as detection techniques improved, as telescopes became more sensitive and observing campaigns lasted longer, astronomers began finding planets at greater distances from their stars, planets more like our own Jupiter. Today, we know of thousands of exoplanets, planets orbiting stars other than the Sun, and a significant fraction of them are Jupiter-sized or larger. Some orbit far from their stars, like Jupiter. Others orbit much closer, like the hot Jupiters. Some have highly elliptical orbits, swooping close to their stars and then swinging far away. Others have circular orbits, stable and unchanging. And each one is a unique world, shaped by its own history, its own formation process, its own interactions with sibling planets, and the protoplanetary disk from which it formed. Studying exoplanets helps us understand Jupiter better because it shows us the range of possibilities, the different outcomes that can result from the process of planet formation. Why do some systems have hot Jupiters, while others, like ours, have Jupiter at 5 astronomical units? Why do some Jupiter-mass planets have highly elliptical orbits, while others have nearly circular orbits? These questions relate to migration, to dynamical interactions between planets, to the properties of the protoplanetary disk. And by studying a large sample of exoplanetary systems, by looking for patterns and correlations, astronomers can test theories of planet formation and refine our understanding of how Jupiter came to be. One of the most intriguing discoveries from exoplanet studies is that systems like ours, with small rocky planets close to the star and giant planets farther out, are not necessarily the most common. Many systems have giant planets close to their stars, or they have multiple giant planets with no clear separation between rocky and gaseous worlds. This diversity suggests that planet formation is a complex, chaotic process, sensitive to initial conditions, capable of producing a wide range of outcomes. And it raises the question, is our solar system typical or unusual? Are we in a common configuration, or are we an outlier, a rare arrangement that happened to produce conditions favorable for life? The answer is still emerging as we discover more and more exoplanets. Current data suggests that systems with a Jupiter-mass planet at several astronomical units from the star are relatively common, present in perhaps 10 to 20% of stars. Systems with hot Jupiters are less common, only a few percent of stars. And systems with Earth-sized planets in the habitable zone, the region where liquid water can exist on a planet's surface, are also common, present in perhaps 20 to 50% of stars. But systems with all of these features together, a Jupiter-mass planet at several AU, a rocky planet in the habitable zone, and relative dynamical stability, may be less common. We are still collecting data, still refining our understanding, still working out the statistics. This is Jupiter, a world of extremes, a world of mysteries, a world that challenges our understanding at every turn. It is a place we can visit with robotic emissaries, but never with human explorers. A place we can study with instruments and telescopes, but never fully comprehend. And yet, it is not separate from us. It is part of the same solar system, part of the same story, part of the same grand experiment in cosmic evolution that produced stars and planets and, eventually, life and consciousness. When you look up at the night sky and see Jupiter, that bright, steady point of light, remember that you are looking at something ancient and enormous, something that was already old when Earth was young, something that will continue to exist long after our sun has exhausted its fuel and swelled into a red giant. Jupiter is a reminder of the vastness of time, the enormity of space, the complexity of the universe. It is a reminder that we are small, fragile, temporary, but also that we are capable of understanding, of reaching beyond ourselves, of touching the infinite through thought and observation and curiosity. The planet that physics can't fully explain is also the planet that inspires us to push physics further, to develop new theories, to build new instruments, to ask better questions. It is a teacher, patient and silent, offering lessons to anyone willing to look, to listen, to wonder. And as we continue our exploration, as Juno and Juice and Europa Clipper and future missions yet unnamed send back data, as computers grow more powerful and simulations more accurate, as our understanding deepens, we will come closer to explaining Jupiter. But we will never fully explain it, because every answer reveals new questions. Every mystery solved uncovers deeper mysteries waiting beneath. And that is exactly as it should be. That is the beauty of the universe. It is infinite in its complexity, inexhaustible in its capacity to surprise us, endless in its invitation to explore. Jupiter, the giant, the enigma, the world of storms and magnetism and hidden oceans, stands as a monument to this truth, a beacon calling us outward, upward, into the darkness, into the light, into the vast and patient cosmos that has been waiting for billions of years for us to arrive, to look, to understand. And now, as we come to the end of our journey, as the words slow and the night deepens around you, let yourself rest in the knowledge of what you have learned, in the wonder of what remains unknown. You have traveled farther than any human will travel in your lifetime, across millions of kilometers of empty space, through clouds of ammonia and ammonium hydrosulfide, down toward an ocean of metallic hydrogen that glows with its own heat. You have visited moons with subsurface oceans, watched storms that rage for centuries, felt the pulse of a magnetic field stronger than any other in the solar system. And all of this enormity and strangeness and beauty exists. It is real. It is out there, orbiting the sun, spinning through space, radiating heat, generating magnetic fields, hosting moons and rings and auroras and mysteries. It is waiting for us to return, to look closer, to ask more questions, to never stop seeking. Let the quiet settle now. Let your breathing slow. Let your thoughts drift like clouds across Jupiter's sky, carried by winds you cannot feel, shaped by forces you cannot see, part of a pattern that is larger than any individual thought, larger than any individual mind, part of the great cosmic pattern that connects everything, from the smallest electron to the largest galaxy, from the briefest moment to the longest age, from the known to the unknown, from physics to mystery, from here to there, from now to forever. Jupiter, the planet that physics can't fully explain, the giant that guards the outer solar system, the world of perpetual storms and hidden depths. Thanks you for visiting, for wondering, for caring. And as you drift toward sleep, toward rest, toward the soft darkness where dreams and knowledge blend together, remember that the universe is vast and patient and filled with wonders, and that you are part of it, connected to it, made from the same atoms that make Jupiter, the same atoms that make everything, stardust and hydrogen and helium and all the elements of the periodic table, forged in stars, scattered by supernovae, gathered together by gravity into planets and moons and you. Rest now. The cosmos will still be here when you wake, spinning silently through the void, waiting for your questions, ready for your wonder, eternal and patient, and infinitely, impossibly, beautifully real. Good night, traveler. May your rest be deep, your dreams be peaceful, and your curiosity never fade. The universe, in all its mystery and majesty, awaits your return.